Good morning, good afternoon, good evening, whatever it is. Welcome to what would have been lecture 18 on March 25th, 2020. And had we been meeting, I think Raging Fire by Philip Phillips would have probably been playing. So cue that up if you are so inclined. And so I got 4 videos for you today. So by the time you're done with all 4 of them, you should be able to describe and determine if something is a state function and kind of say about what that means to be a state function. You're going to be able to describe one state function in particular called enthalpy. You're going to be able to relate amounts of reactants and products to the heat evolved given a thermochemical equation, and you'll also know what a thermochemical equation is. You're going to learn about something called Hess's law, and you're going to use it to determine the enthalpy change of a reaction given a series of known thermochemical equations. And lastly, you're going to be able to determine the enthalpy change for any generic reaction given a set of standard reaction enthalpies of formations. And all of those words will mean something to you, I promise. So let's get going. So, what is a state function? State functions are one of those things that are very difficult and almost impossible to define. It's just better, easier to give you an example. So I'm going to give you one. Temperature. And the question is, does the temperature of an object, if you were to measure it right now, depend on what temperature it was yesterday? Now, I'm not talking about it being in the same oven or the same ice bucket or something like that, but just, if you're going to take the temperature of something right now, does the temperature that it had, yesterday make any difference? And the answer is no. If you're going to measure the temperature of something, all that matters is its temperature at that instant. And that's how state functions work. Now, in thermodynamics, very often we are talking about a change in a state function or a state variable like temperature. And this requires just a slight change in the explanation or the example. So let's talk about a change in temperature. And then the question is, if you were to measure the change in temperature of something, does it depend on the starting and ending temperatures, or does anything that happened in the middle matter? And the answer, of course, is not really. So in thermodynamics, we often refer to as this delta, which always means final minus initial. So the change in temperature, delta T, is equal to the final temperature minus the initial temperature. And that is it. So, if something was 30 degrees at the end and was 20 degrees at the beginning, the change in temperature is, just 20 degrees. And whether it went down to negative 100 degrees or positive 1 million degrees in the middle doesn't actually make a difference. So again, the change in temperature only depends on the initial temperature, the final temperature, and not in any one of the immediate or intermediate temperatures at all. So that's a state function. So the practical definition in thermochemistry is this one right here, that the change only depends on the final and initial values, nothing in between. So let me talk about another very common example to see if you can figure this out. All right, so here's an example, and I've drawn up here a Google map of Albuquerque and the surrounding areas. So let's say that you are somewhere near the Big I, and you want to get to Sandia Crest, which is about right there. And could propose a couple of ways to do it. You could, walk up on Broadway, hit Tramway, go to the tram station, and then just take the tram up, and the crest is somewhere about right here. That's one way. Or you could, admittedly illegally, walk by I-40, go through the pass, take 14, and then hike up 536 till the crest, getting out there from the east side. And so those are 2 ways to get there. And I'm going to ask you some questions, and this would have been on the group activity. So there's the map still there. So the question is the distance that you walked from, let's say, the Big I to Sandia Crest, is that a state function? And the answer is no. The actual distance that you've walked, number of steps, miles, however you want to count it, actually depends very much on the exact path you take. So that is an example of not a state function. Now, what about the actual distance from the Big Eye to the Sandia Crest? Not the distance that you walked, but the actual distance between that point by the Big Eye and the Sandia Crest. Is that a state function? So hit pause, think about it for a second, and then come back. All right, and it turns out the distance actually is a state function. Your starting point and the tram station at the crest are fixed points in space, so their difference is a fixed point in space. So the difference between those 2 points doesn't matter how you traversed between the 2 points. All right, settle point. But what about the height difference? Now, these are two very different ways of getting there that have very different changes in elevation, but again, so you started out at roughly 5,000 feet at the Big Eye, and you get up to about 10,300 feet. So is the change in altitude, the height difference, a state function? And again, that answer is yes, for the same reason as 2. The height of by the Big Eye is a fixed amount. The height at the top of the Sandia Crest is also just a fixed value, and their difference is also a fixed value. So it doesn't matter which route you took, the elevation change is the same. So the distance that you walked is not a state function. The distance between the 2 points is, and the elevation change or the height change also is. So this hopefully will give you an idea of things that are what's a state function and what isn't. So now I want to bring back something from quote-unquote yesterday's stuff, and that is this thing called internal energy, which depending on what source you're looking at, sometimes it's U, sometimes it's E. I kind of like U. Now, we said that the change in internal energy of something is equal to, we talked about 2 ways that can change, and that's heat can come in and out, and work can either be done or be done to the system. And if we simplify life a little bit and say that those are the only 2 ways to change internal energy, you could say that the internal energy change of something is equal to the sum of the heat transferred in and out, or the work done. And you can see that you'll note that this delta U has this change symbol, the delta, in there, but these don't. So heat and work, by definition, are transferred quantities, so the delta is actually kind of redundant. So in English, we would say that the total change in internal energy is equal to the heat transferred and the sum of the work done or received, however the direction is going. So let me propose 2 routes to a chemical reaction. So if you take a mole of octane and react it with 25 halves or 12.5 moles of oxygen, you get 6 moles of carbon dioxide and 9 moles of water and quite a bit of energy, which is why we burn it. So because this process gives off energy, and we say that the reactants are at a higher energy state than the products, and as you transform from the products to the reactants, that difference in energy is given off. Now, the question is, how is it given off? How is that manifested? And the answer is, well, it kind of depends. You could, if you had nothing else going on, take that gallon of octane, which would be essentially, this is the main component of automotive gasoline. And if you were to burn it in a steel barrel, all of the energy, just about all of it, would be given off in the form of heat. But let's say you were a little more sensible and at least burned it in the engine of your car, so you at least got something useful out of it, the mechanical motion. Oh, well, then this is different then. That this energy change is harnessed in a way in the car such that some of this energy is converted to mechanical work, making the car, go forward in some direction, and some of it is given off as heat. Now it turns out that it is very difficult to avoid the loss being some of the energy given off as heat. Actually, it's impossible to lose that. It's a very annoying rule of this universe that we happen to live in. But clearly there's a difference here. In the barrel, it is all heat. And in the engine, a bit of it's mechanical work and the rest of it is heat. So this is an example of these two actually not being state functions, because whether it's burned in the conditions of in an open barrel or in an internal combustion engine, there's a difference. Now, in either case, the change in internal energy, whether you're calling it U or E, is the same. It's determined by this point and this point right here. And that is a function of just the properties of octane, oxygen, carbon dioxide, and water. But the work is different, which means that, and if the change in internal energy, if you go back to the previous slide, if that change in internal energy is equal to their sum, right? So if one changes, the other has to as well. So this tells you that while the change in internal energy is a state function, the heat and the work are not. But interestingly enough, their sum is, as long as heat and work are the only ways that the energy change can be manifested. And for a great many processes, that's actually true. So let's talk about those not state functions anymore, namely heat. So it's unfortunate that heat is not a state function. I should tell you that physicists and chemists avoid non-state functions like the plague. But it's unfortunate because heat is a very convenient and easy quantity to measure. But let's place some constraints on the reaction that we're running. Let's say that the reaction is done in a constant volume, so you actually do it in a closed container that is rigid enough not to explode. So we talked about work the other day, and we expressed the work simply as the product of the pressure times the change in volume of something. Now, if the volume is constant, then this delta V term is 0, which means the work is 0. So we said before that the change in internal energy of something is equal to the product of the heat and the work of the process. And if the work is by definition 0 under these cases, then delta U is simply equal to Q, the heat. And if we invoke constant volume, so a lot of times in thermodynamics, if you see a variable as a subscript, that means that variable is being held constant. So under constant volume conditions, heat actually is a state function and is equal to delta U. All right, again, as long as the volume is constant. Now, it turns out that running reactions under constant volume is actually not the most convenient way to do things, and in some cases not particularly safe. Most experiments are formed under constant pressure, namely they're in an open beaker open to the air, so that constant pressure happens to be atmospheric pressure. So let's see if we can't make something fun happen with that. And yes, I know fun is subjective. So let's think about what the Q would be at constant pressure. And again, so we're going to invoke constant pressure, so we're going to put a little subscript P on there. So the internal energy is equal to the constant pressure heat plus the work done. So we can, and the work we said is equal to whatever the pressure is times the change in volume with a negative sign in front of it. So we can say that delta U is equal to, QP minus P delta V. And we could rearrange that to have an equation that says the heat is equal to. And if you do that, the heat is equal to the change in internal energy plus the product of P delta V. Now, this is important. All of these, internal energy, volume, and pressure, they are all state functions. And it is a very useful and important rule of thermodynamics that if something depends only on state functions, that thing must be a state function as well. So if you invoke the constriction of constant pressure. And the reason why this works is because this expression for the work only applies at constant pressure. So since everything in this expression here is a state function, that means the heat transfer under constant pressure is also a state function. And this is thought to be an important enough result that this quantity, delta U plus P delta V, is given its own name, enthalpy, delta H. And if you're wondering why the word enthalpy is symbolized with H, it's because it's German. But more importantly, it is a new state function. So in English, what is it? So enthalpy is an energy-esque thing. It has units of energy, and it is equal to the heat transferred for a process, either in or out, under constant pressure conditions. Another way of saying that is that it represents the energy change, the internal energy change of a process that is not expressed as mechanical work. And mechanical work here is usually the expansion of a gas. All right. So that's it for this video. I will see you at the other one.